Hi, I'm Kevin. I'll present you the work I did during this last 4 years during my PhD at Imperial College, and that's a work in collaboration with lots of people that you can see on that slide, and both from King's and Imperial. So my main goal was on automatically finding the fetus in MR images. A quick overview of the talk. I'll give some background on fetal magnetic resonance imaging and Python for medical imaging. And then I'll show you the method I came up with to automatically find the brain and then automatically find the rest of the body of the fetus. So that's an MRI scanner. Mainly, it's a huge magnet, typically 1.5 Tesla. It's safe compared to CT or X-rays, so you can use it during pregnancy. It provides high-quality images, but unfortunately, it's a really slow acquisition process. And so that's some examples of fetal MRI. As you can see, the fetus moves during pregnancy, and imaging data takes time, and so you have to deal with this. And my task is to automatically find the fetus. The problem is, well, the fetus, it's an object in 3D, and it can be in any orientation. I mean, that's the bladder of the mother, so you know that the head is there and the legs are here, but the baby can be upside down, whatever. And also, you can use MRI on the fetus from 20 weeks to 40 weeks term. And that's at 20 weeks, and that's at 40 weeks, so you've got a 50% increase in size. All the organs are the same, but the relative size, the contrast patterns, things are different, so that's the complexity I have to deal with. So because the fetus moves, when we acquire data, acquiring a whole 3D volume will take too much time, and the fetus will move, you'll get rubbish. So instead, you acquire lots of 2D slices, and you stack them, and you obtain, so that's the native slices. And when you stack them, you can see that the fetus moved between slices, and you end up with those jigsaw artifacts. So what you can do is actually acquire several stacks of 3D slices, and if you can, and you can segment parts of the fetus in those images. So here we've segmented the brain, and my work has been on doing this in an automated way. Once you've got these segmented parts, you can combine them from several volumes acquired in different directions and obtain a higher resolution volume. And you can also do this for other parts of the body. So Python for medical imaging. The nice thing with Python is that you've got this huge ecosystem of packages, and most of those modules come with the communities behind that can help you, the code that you can dig into to understand better how it works, fix it, add the 3D version if you don't have it, if they don't have it yet. Yeah, so I guess you already know most of them. The one you might not be aware are, let's say, OpenCV, very famous for computer visions, mainly C++, but automated Python wrappers. VTK, very good for visualization. Most of you probably know Maya VI, which is built on top and provides an easier interface. And simple ITK, which is a simplified interface to ITK, ITK being a medical imaging library. So let's talk about medical imaging libraries. What's a medical image? It's an image, but most of the time it's 3D or 4D, 4D being 3D plus time. And with that image comes spatial information, because you want to acquire different scans of different parts of the body, and you want to be able to relate one to the other with scanner coordinates from the scanner, so that you can overlay images, and when you want to combine them and merge them, you don't start from, you start from an initial alignment, and then you can refine it. I've been working with IRTK, not ITK. IRTK stands for the Image Registration Toolkit. And why did I use that package? The main reason is I'm doing a PhD in a lab. I want to use the same tools as my colleagues. Most of them don't use Python, but I want to use Python for, let's say, all the modules I presented you before, and other reasons you might yourself know. Yeah, so if you use the same backend as your colleagues, then you've got the same features, the same conventions, because in medical images you've got conventions, what's left and right, for instance. And you also have the same bugs. And that's important because you do half of your pipeline in Python, suddenly you do the second half in C++ and things don't work anymore. Where's the problem? Well, if you were using the same backend from the beginning, things wouldn't be working in Python. And then you would have debugged it, and you see what I mean. And also, IRTK provides state-of-the-art algorithm for aligning images. So the way I interface IRTK with Python was through Cython. I defined a medical image being a subclass of a NumPy array, and with it comes an attribute, which is a dictionary holding the dimension of the image, the orientation, the origin, and the pixel size. Let's say 1 pixel is 1 millimeter by 1 millimeter by 4 millimeter. And so I access IRTK through Cython. The benefits of doing this wrapping myself is that compared to, let's say, a Swig interface where C++ objects are automatically mapped to some Python stuff, the benefit of having a subclass of an NumPy array is that I can overload get item, so that whenever I crop an image, the spatial coordinates are updated. Whenever I slice it, same thing. And as you see with my problem of finding organs in different blocks, 3D volumes, and then merging the volumes together, I'm very interested in preserving those 3D coordinates. And you also want to preserve those coordinates when you do some resampling. Otherwise, I mean, otherwise you could just use a SciPy ND image resample, but that stuff won't preserve your coordinate system. So the main thing when doing this interface between Python and C++ to Cython was to write conversions between IRTK and Python, so that in Python I've got my NumPy array, give it to Cython. In Cython I split the dictionary into the pixel size, x-axis, y-axis, z-axis. So that's the orientation, the origin, and the dimension. And when I speak about the dimensions, that's because your NumPy array has a shape, but you can squeeze your array and remove the flattened dimensions. But in C++, everything, I mean, at least in IRTK, it makes simpler if everything is a 4D array. So that, that's much simpler. So once you've got this mapping between a Python object and C++ object, then all the rest is straightforward. On one side, you write Python code, on the other side, you write C++ code. So now let's talk about machine learning. The reason I went for machine learning is what you do in machine learning is learning from annotated examples, and you generalize from a training database to new subjects. And that way you can implicitly model variability such as the age or the pose. The fetus is an articulated body. Or let's say the background, in my case, maternal tissues. Compared to other problems you might have heard of in machine learning, I've got to face the fact that I'm working on small data sets. What I'm learning on is actually the voxels. But in terms of fetuses, subjects, pregnant mothers that have been scanned, I only have like 50 of them, roughly. So what I did was, let's infer the size of the things we are looking for from the age of the fetus, because we roughly know it when we scan the mothers. So before you can do machine learning, the first thing you need to do is build your training data sets. So I had like 450 3D volumes. That's because we've got several volumes per subject. And I wrote a tool using OpenCV to quickly browse all those volumes, crop my boxes, and I end up with this. So that's the native slice, and that's the orthogonal direction with where you can see the noise. Luckily, when I was working on the full body, I benefited from previous work from Melissa Damodaram, who did a study on growth restriction. And when she was doing that study, she manually segmented the fetuses, and that's the kind of data I used when learning how to find the body of the fetus. As you can see here, there are striking staircase effects, and that's because she was working on fixed slices. Like every slice is separated by 4 millimeters. So now I'll present you the method I worked on to find the brain of the fetus. So let's say that's our image, and the goal is to find the brain. So I worked slice by slice. So for every slice in your volume, I started by detecting maximally stable extremal regions. That's in order. I do it in order to pre-select some regions, and then I filtered those regions by size because I know roughly the size of the object I'm looking for. And then I use a bag of words model. So I trained an SVM on histogram of 6 features, and it gives me this classification: not brain, brain. And because I do this in every slice, I need to do some accumulation of the votes in 3D to obtain a best fitting place for my bounding box. And I use RunSack for that, where you randomly select a few candidates, you fit a box, and then you check how many in the rest of your candidates fit into that box, try it several times, and take the best box you found. In terms of size constraints, the way I filtered by size was using the occipitofrontal diameter and biparietal diameter, which are common measurements that are performed during ultrasound examinations. So, but I know the age of the fetus, and I know the growth curves, so that's how I get the size. In terms of evaluation, so in red is the ground truth, green the detection. If we compare the center of both boxes, the median error in a 10 leave 1 out cross validation was 5.7 millimeter. In all cases, we had an overlap larger than 70%. And if we were asking for the whole of the brain to be included in the detected box, it happened in 85% of cases. And so the runtime here for this method is less than a minute on a desktop PC. Some examples of the worst cases, and those ones, and it happened because of the presence of the bladder of the mother, which shares, similarity in terms of intensity patterns with the CSF in the brain. CSF being the liquids in the brain. So now I'll speak about the method I developed to find the body of the fetus. So again, to illustrate the problem, we've got our data, and we want to find where the body is. So localizing the body is a little bit trickier than finding the brain. And I can't just use the work I did on the brain and train on, change the training data and apply the same method. It doesn't work because the intensity patterns are different, but also because the shape and the size are different. So here, that's the brain and the lungs, and you can see the size difference. And you can also see that the brain is roughly an ellipsoid, but the lungs are have a very irregular shape. So if you slice the brain in whatever direction, you will always end up with an ellipse. But if you slice the lungs, you can end up with a banana. You can end up with two disconnected components. You've got something very irregular. So that's why I chose to use a 3D approach in that case, despite the motion corruption. So for these methods, what I did is first a size normalization based on the age. I look for the organs in a specific order, and I use image features, which are steered by the anatomy of the fetus in order to account for the unknown orientation of the fetus. So that's our fetuses from 24 weeks to 38 weeks. You've got this increase in size, and we normalize the size. So if they are already segmented, it's quite easy to just stretch the images the same way you would do with ImageMagick. But given a new subject, the only thing you know is the age of the fetus. You don't know where it is in the image. So what you can use is the Keraudren length to resize your images. So the distance between the top of the head and the buttocks. So I said I'm looking for the organs in a specific order. I used the method I worked on previously to find where the brain is. Once I know where the brain is, I know that the heart must be within a specific range from the brain. Once I know where the heart is, I know that the lungs and the liver must be within a specific range from the heart. And those ranges, I can define them independently of the age of the fetus because of the size normalization I mentioned before. And when you do machine learning on images, you need features. You can't just use pixels like this. So the kind of image descriptors I've been using are mainly simple difference of mean intensities. So you take one 3D patch, another 3D patch, both are at a random offset from the current pixel. You check, is the first patch brighter than the second patch? Yes, it gives you 1. Yes, it gives you 1. Another patch, it gives you 0, and so forth and so on. And that way you build a descriptor, and that for this pixel, this will be the input of your machine learning algorithm. And why do we use that kind of features? Well, several studies show that they are descriptive enough, but also they are very nice to work with because they are easy to compute. This can be done with the integral image. The integral image is a representation of the image where every pixel in the integral image is the sum of all the pixels to the left and above in the original image. So at 1, you have the sum of all the pixels in A. At pixel 2, you have all the pixels in A and B. At pixel 3, you have the sum of A and C. At 4, you have the sum of A, B, C, D. So let's say what you want is D. To have D, you start by pixel 4. Then you remove pixel 3 so that you remove A and C. Then you remove pixel 2 so that you remove A and B. But you removed A twice. So you add it again. And that way, in just 4 table lookups, you get the intensity. You have the sum of all the pixels in a patch, independently of the size of that patch. And if you just want the mean, then you just divide by the dimensions of that patch. And in 3D, it's almost the same thing. It will be in 8 table lookups. And in terms of Python code, it's 3 successive calls to the cumulative sum. So I said I used features which are steered by the anatomy of the fetus. So at training time, I use features which are extracted in the coordinate system aligned with the anatomy of the fetus. And at testing time, when I'm looking for the heart, I rotate around the brain. And that way I know that when I'm at the true position of the heart, I am roughly in the same configuration as at training time. And once I have a candidate hypothesis for the heart, I just fix the heart to brain axis, and I just have to rotate randomly around that axis to find the other organs. So the approach I used is based on the Hoff forest. So it's a combination of classification step and regression step. So first, I classify every voxel within my range. Is it heart or not heart? And I get this probability map. Then I do a regression step. All the voxels that are assumed to be heart vote for the location of the center of the heart. And that way you have an aggregation which happens. And then you have a much better estimate of where the heart is. So you do this for the heart. And then you do this for the other organs. You've got first a classification step, which is followed by a regression step. So what I'm actually showing here is the back projection of the regression votes. So I've got one brain location, but I formulate different candidate hypotheses for where the heart is. For each heart, I formulate candidate hypotheses for where the lungs and liver are. And then I optimize the spatial configuration of the organs so that I maximize the detection scores, and I also maximize the score based on the relative position of organs, because the left lung should be to the left, the right lung to the right, the liver below, or this relative to the position of the heart and the brain. A little bit of Python code. So I worked with scikit-learn and pre-computed my features. So at training time, you need to get started by selecting a random set of sizes for your patch tests and offsets. Then for all your labels, you extract your features and put them into X and Y, and you loop over all your images. And lastly, you call the feed function of your random forest classifier. So what's really nice with when you work with Python is that the math gets really easy to write. You write it on your keyboard the same way you would write it on paper. So in terms of this coordinate system, which is rotating, where you've got your arrays of current pixels, and you've got the brain center. So you've got your current pixel here, and you've got your brain center, and you want to define this rotating coordinate system with some randomness in it. So first you start by computing the vector from your current pixel to the brain. Then you normalize it. Then you take another random point. You project it on the plane orthogonal to your first vector. You normalize it. You do your cross product, and that's it. You get your coordinate system. At testing time, well, when you pre-process your features, when you pre-compute them, the problem is you're working on the 3D volume, so you can't pre-compute your features for all your 3D volume at once. You would run out of memory. So the trick I used was by first I list all the voxels where I want to evaluate my classifier, and then I split it into chunks. That way I have a trade-off between memory consumption and the cost of going back and forth between the Cython code of scikit-learn and the for loop of looping over my set of pixels. In terms of evaluation, I evaluated it on 2 data sets, but mainly the first one was more for training. Was the one I used for training, and the validation was done using leave one out. The second data set is much more challenging, and it actually corresponds to the one I'm interested in, the one we use for motion correction. And the key message is that in 90% of cases, in all those cases, the detected heart center was within 10 millimeter, and that's roughly enough to fit a box and get started with the cropping and the motion correction. But the main problem is the runtime. Here for that method, I end up with 15 minutes. And so you might think, oh, that's a cheat. You're wasting your time listening to me right now. Especially if you heard about the Microsoft Kinect and you say, but this guy is doing like similar stuff. Yeah, I'm using similar features on random forest, and that's the same approach they do in Kinect. But in Kinect, they do it real time. So what's wrong with my approach? In Kinect, they work with 2D images. And I've got 3D volumes. And they work with a fixed orientation. I've got to do this or this rotation search, and but mainly the real problem is that I've been pre-computing those features and using scikit-learn, which is very nice because you can apply it to anything, but it's not specialized for image processing. So the first step in optimizing my code would be to tweak the parameters, reduce the number of trees, reduce the number of features, choose the accuracy versus runtime. But this will be, even after this, it will still take several minutes. So if I really want to be fast, what I need is a random forest implementations, which was built for sliding windows, so that at every pixel you can you have a sliding window object which points to a single copy of the image, and your random forest is templated over the type of points so that it can accept a sliding window point. and the type of tests, so that it can do these batch-wise tests. And that way, you would be computing tests on the fly. Depending on your path that you take down your trees, you would compute a different set of tests. With such an implementation, which I actually used in a different project, you can do your multi-threading over the slices of your 3D volume, because if you do your multi-threading over the pixels, you don't benefit from the actual multi-threading. And well, when you do start toying around with the multi-threading in Python, you end up with a lot of copying data into memory, and I mean duplicating objects into memory, and it's not that nice. So some examples of localization results. On the left side, you've got the original data and a denoised version on the right side. In blue, the heart, red, the left lung, green, right lung, yellow for the liver. So what you see are cloud points that correspond to the back projection of the regression votes. And it's a cloud, and it's not a continuous blob, because you've got those random trials. So you've got discontinuities in your prediction. And the benefit of the denoising, you can mostly see it when the baby moves a lot, and you end up with those dark slices. The denoising attenuates it, so it's a median filtering. So yeah, and in those examples I showed, the idea is to show so that it works whatever the orientation of the fetus, because you're doing this actual 3D search. So to conclude, I presented you a method to, some methods to automatically find the organs of the fetus in MRI. I've done most of it using Python, finding the brain, the heart, the lungs, and the liver of the fetus. And I've trained only one single model across all ages and orientation of the fetus. And all of this, I did it thanks to the ecosystem, the Python scientific stack. So from OpenCV, I used the maximally stable experimental regions and the SIFT features. From scikit-image and SciPy and the image, I benefited from lots of image processing functionalities. From scikit-learn, I've used the support vector machines and the random forests. And for everything I was missing, then I used Cython to get it from C++ because it was already available in C++. So thanks a lot for your attention, and for more information, source code, you can check out my website or GitHub repository. And if you have any question, I would be happy to take them.
What is the application of this?
So the main application is what I presented at the beginning. The fetus moves, you're carrying several stacks, several 3D volumes, and you want to merge those volumes. But when you merge those volumes, you need to exclude the mover from the image, because the fetus moves independently of the mover. So
would the physician be using the information about where to locate the brain, or would it be the mother, or who would actually use it?
The clinician.
Look at an X-ray or MRI scan, he can intuitively locate the brain already. So who would actually use that piece of information?
What the clinician wants to look at is also, he wants, currently most of them, they look at the slice by slice data, but also they would like to be able to look at it as a 3D volume. Reslice it in any direction, rotate it in 3D, and for this they need to do this motion correction. And for this motion correction, currently they need to do some manual segmentation. So that's where I come in and I say, hey, we could do this manual segmentation automatically.
It's actually very similar to the question I was going to ask. I was going to say, have you actually shown this to any clinicians? Have you had any feedback from them that they gone, oh, that's how that's. Because the way you say it is interpreting a structural scan,
yeah,
which a lot of clinicians would use their own intuition to look at. I'm just wondering if you've had any feedback so far.
Yeah, so that's the kind of tool they think very, very useful. I know some people in one lab have been using it. People in my lab, there's one they've been using it a little bit, but there's still one thing which is missing, which is when you work on the brain, if the fetus moves a lot, those coordinate systems you get from the scanner, they're not enough to initialize the motion correction, because if you move too much and there's not enough overlap between the images anymore, realigning them doesn't work well. And in that case, what they do is actually manually initialize this alignment. And in that case, well, they don't really need my work. And so something which is missing from what I did is this finding the orientation as well of the brain, so that I could help them align these images better.
And once they can locate the brain and form the 3D structure, I mean, what do they do with that information? Do they try to identify abnormalities, or?
So they will check at the size of different regions, for in particular the ventricles, for instance. But also a lot of this research, a lot of this is like some of this is for clinical application, but most of it currently is for research, and we do this on healthy subjects, and we are trying to understand how the healthy brains develop, and also once you know how the healthy brains develop, you want to compare it to preterm babies, and also yeah, no, that's it. Would you have any other questions?
You mentioned that you were using, you started out looking at Python and the different libraries, and you kind of used more kind of C as you went through. If you didn't have constraints for the rest of your lab, would you try and port more of it to Python, or would you port less of it to Python and move all the way to C?
I would. I think the right solution is a trade-off between both. Because I mean, you can't loop over pixels in Python, but you cannot do everything in C++. And I would say lots of people use Python in my lab just the way you would use Bash. They code lots of binaries, and Python is just to list their files, do some regular expressions on the file names, and then open a CSV file, and then call the C++ binaries. I mean, we need both. And all the motion correction code, I doubt it will ever be written in Python. And that's a pure C++ code, and it has been recently ported to CUDA.
Yeah.
And that's, I mean, so you need to, for a pipeline like the one I did, you need Python. But for something which is very specific, then you need C++.
So without your lab constraints, you'd probably still do the same solution. Like, you're happy that it's actually a pretty optimal solution.
Yes, but since I came, it seems that more people are switching to Python instead of MATLAB. But we still need the C++ behind.
Yeah, thank you.
Welcome. Any more questions? So thanks a lot for your attention, and